All right, in this module, we're going to start a new chapter on the mechanical properties of materials, and I want to sort of introduce you to this topic before we go any further. So, in this in this class, really, we started out by looking at the atomic structure, and then we built up to the structures of materials. And now we're going to look at the properties of those materials. And the idea is we want to look at these properties and with the idea that, if we change the structure or the material, the properties will change. And so we don't have time to talk about all the properties listed here, like thermal properties, electric, mechanical, or sorry, magnetic, optical. So we're going to use mechanical properties as a way to talk about properties in general and how they connect back to atoms and the structures and so forth. So that's kind of what we're doing with this chapter on mechanical properties. So we're going to focus on mechanical properties. All right. So when we talk about mechanical properties, we need to know how we get those properties, right? We're not just going to go through and list off the strength. Sorry about that. We're not going to just go through and list off the strength and modulus and so forth of given materials. We want to talk about how we obtain those properties so that we know a little bit more in depth, just more than just the number. That's what this class is about. And so those properties, for the most part, when we talk about mechanics, are determined by tensile testing. And so this is a typical tensile tester or load frame that we have. And so what we have is we have our specimen that we want to test its properties, and then it is basically attached to two fixed positions on this load frame. So you can see kind of the screw grips that locks it into place. We have this thing called an extensometer attached to our sample so that we can measure how far apart it stretches under the tensile load. And then we have a load cell, which measures the force required to move a given position. So we're basically moving this crosshead downward, pulling apart the sample. Pulling apart is another way of talking about tensile stress. And so by moving it, we're going to have to exert force. That force is measured by the load cell, and the distance it moves is going to be measured either by the crosshead motion or by this extensometer on the sample itself. So that's in general how we test this. And this crosshead moves either by threads or hydraulics to kind of extend or pull apart this specimen. The load cell measures the force, like I said, the extensometer placed to measure what we call the elongation. The sample itself that we test is going to look something like this. And for shorthand, you'll often hear the term dogbone used because of its dogbone shape. We have the grip ends. This is what's in the machine being gripped. And then it tapers down to a reduced section so that is the portion being tested. And then this portion is for grips. So this is circular. This has a circular cross section here, but we can also have rectangular sections. So we have the grip portion. It has the greater diameter to avoid fracture there, and then a reduced section. And so that reduced diameter concentrates the stress in this section. And the gauge length is inside the reduced section, and it's just a standardized length. So, for example, this is 2 inches and it's slightly longer, less than the reduced section, and it's the standardized length. So we basically measure this before the test and after in order to calculate ductility, which we'll talk about in a later section. And the cross section, we're going to need this for further calculations as well. So I thought it'd be useful for you to kind of see a test in action, what this tensile test looks like. So we're going to look at a quote unquote real tensile test. And so I thought I'd have some fun with this. And so around Easter time one year, I bought this giant 1-pound gummy bunny. So this is made out of gummy bear material, right? And so what I did was I put it in a pot chopped it up, melted it down, and then cast it into a sheet in a pan. And then I cut it with a dog bone punch into that dog bone shape that you saw before. And here's me taking a length measurement of that dog bone. So then I attached it just like we would any other dog bone into the machine, and we tested it in tension. And so here's that video. So this is the gummy dog bone that you can see, and then these are the grips. And so in this case, the grip is going to move upward in this direction. That's the crosshead. And then there's a load cell up here measuring the force it's going to take to move this. So I'll go ahead and play this. We might have to speed it up so that you can, it's the video's already sped up quite a bit. And so you can see it extending quite drastically. So this is the elongation that we want to measure for this sample. And eventually, this one extended so much that it actually came out of the grip. And so we didn't have a very successful test here, but this is a very long extension for most of the materials that we're looking at. And so the result of that was a load versus extension plot, right? So if you extend it some distance, what force or load does it take? So this has extension has units of millimeters, and the force here was in kilogram force. And so this is what it looked like. So if we extend it, we have to apply some amount of force, and that force keeps going up the longer we extend it. And then at this point, it either fractures or the test is over, so it goes way back down. Right. So that happened for this sample that you saw before. But then it brings us to an interesting question is, so you're in your lab and you make a gummy dog bone that looks like this. Well, somebody else in their own lab makes a bigger one. They want a bigger gummy dog bone. And so they test it like that. Well, the problem with this is that by increasing the dog bone size, if we look at this result here, well, if it's a bigger sample, if the sample size is doubled, then the resulting extension and load would also increase. And so if we're trying to compare the mechanical properties of this gummy material, they're getting altered by the specimen that we choose, by the sample size. And so this isn't good. So basically we need a way to normalize the data, right? And that's what we're going to talk about in the next module. We're going to talk about stress and strain.